Hello teacher, our team is conformed by Brenda, Gabriela, Paulina, Jasmine, Andres, and me, Alan. We are going to explain you how does the Doppler effect is. The Doppler effect was proposed by Christian Doppler in 1942. It is the change or the appearance of the change of the frequency that is caused by the relative motion between the observer and the source, and that you could say it like you hear something different, but it is not different at all.
When the listener and the source are fixed, the listener hears the same frequency than the source. For example, like this.
We have a listener and a source, but both are in movement. When the source is in movement, it has a velocity, Vs, and the rapidity of the wave relative to the medium is still being V, and we have it in all the directions. Because it is determined by the properties of the medium, in this case the air, and doesn't change because of the movement of the source. But this effect has to do with the wavelength, because it changes according to the relative movement. The time it takes to complete one cycle is called the period, and it is represented by U divided by frequency of the source. During this time, the wave travels a certain distance, which is the velocity multiplied by the period, or the same, that is velocity over period. And the wavelength between two crests, and the wavelength is the distance between.
So in this case, the listener will be standing still, and the source in here will be moving. So, given the formula we've talked about, in here the velocity of the listener will be 0. And with an example, let's say that the source is moving at 3 meters per second, then the velocity of the listener will be 0 meters per second, and the velocity of sound will be 340, and the frequency at which the waves are moving is of 300 hertz. So it will be 340, which is the velocity of the sound, divided by that same velocity plus the velocity of the source, and multiply times the frequency, which will give us 276 hertz. So that would be the frequency at which the listener will receive the wave. And the most common example is, for example, in the car races, where the listener is seated at a given point, like at the benches, and then the cars will be moving on the track, and they will listen different wavelengths for the sound that the car is making.
In this case, we are going to explain when the source is fixed and the listener is moving. Because the source is fixed, we don't use the velocity of the source, so this velocity is 0. Like in this example, where that says a fixed stop siren emits a sonoidal wave with a frequency of 300 Hertz. The listener is moving at 330 far away from the source. What are often hear the listener? In this case, we have the data, and the velocity of the source is 0, but we have the other data. So the formula that we use is the formula of the Doppler effect, but we cancel this term, and we have this, that the listener hear at this frequency. When the velocity of the listener is bigger than 0, the listener is getting away from the source. But if the velocity is less than 0, the listener is getting far away from the source.
When the source of the sound is moving away from the listener, the factor that multiplies the frequency is less than 1, therefore the frequency is smaller. But when the source is moving towards the listener, the factor is more than 1 and therefore the frequency is higher. And during this PBL, we have been studying the Doppler effect through the sound. Nevertheless, sound is a wave and this effect is a property of waves. The simplest way to study the effect is with sound because there are many clear examples, like the one with the ambulance. But we know there are many other phenomena in which the Doppler effect is observable, and also we can solve many problems finding data through this effect. For example, radars work by sending waves of constant frequency, but when those waves bounce in moving object, the radar can measure the frequency of that bounced wave and therefore measure the velocity of the object. The same that happens with echocardiograms. Light also behaves like this. That's why in astrophysics has allowed to study some properties of the stars and galaxies. But we can't observe that change in color with eyes. But we know that when the object is moving in weight or close in respect to the observer, the color the observer perceives changes. It's green when they come closer and orange when they go away. And as the problem statement says, it's possible to measure the velocity in which the universe spans. And even though there isn't any matter which emits or reflects light in the edges of the universe, it can be measured by some other waves, like radiation. Studying this effect has been very interesting since each observer can perceive different things relatively to its position and velocity, and also because of the great amount of usage that we can give to the waves, knowing this effect.